Hello, testing 1, 2. Hello? Testing 1, 2. Oh, that was it. My last time. So if I go ahead and yeah, so you can hear it. Fine. I think the sound is fine.
Do you need a whiteboard? Yeah.
Yeah, well, I can do this. We'll pull the whiteboard out. So how do I link people to this? Yeah, send the link to like that.
see a video camera. I don't see a video camera. I hear one. Oh, hey. Hello, Internet. I'm Isaac, a Golang developer at Movio.
The only thing I haven't got is spare batteries. Do we have batteries in the stationery cupboard? I'm going to look into that. It seems to last forever. I could only find how to construct an embed link knowing a channel ID. I don't know the proper I don't know the proper link. But
Actually, it might not be that important to capture it. I don't know. Don't worry about it. East. Not better. But I'm gonna be far away when I'm. I think this should stay here. Turn it on? Oh, it's on. It's on. Alright, we're almost there. Hello. What's up? All good? Just waiting for the CTOs to come and stuff. Yep. Where's Jonathan? I need Jonathan. Testing 1, 2. Again. Testing 1, 2. Okay, we done? Ah, yeah, please.
Hey guys, happy to see you guys again. Thank you. So this is Mariano. He's going to talk to us about homeless gophers. We're going to have pizza later, and
If you don't follow along the last exercise, you don't get pizza. Sorry. Okay, thank you. Thank you for coming. You know, especially the ones who came from very far. Yeah, so help Gofi find a home, loosely based on a true story. So my name is Mariano. Thank you. That's my true name. I'm a software engineer squad leader according to this, and I'm going to ask you to help me help Gofi tonight, because Gofi is getting evicted. Well, he's not actually getting evicted. He's just that his rent is going to increase by $150 per week. So in addition to what he's having to pay at the moment, that didn't happen to me. That's not why I made this. Actually, you know what? Let me. I feel a little bit overwhelmed by having so many geniuses looking at me and asking for me to entertain you. So I'm gonna hold on a second, replenish my mana. I'm just gonna tell the story of why I made this presentation, right? So in my last performance review 6 months ago, the guy, the CTO of the company told me, hey, if you wanna, forward your tech career, you should do a presentation. And I said, oh, I'll think about it. That was 6 months ago, so I thought about it for a lot of months, and then eventually the CTO sort of like couldn't take it anymore. He quit the company. Then he became the CTO of SB Bank, and he's sitting right there. Thank you for coming. Come on. Okay, that's it. I have my mana at the top now. I can continue. So, so his rent increased a lot, so Gofi has to move. Yeah. So Gofi lives in Gopherland. Gopherland is a land full of gophers. At all times in Gopherland, there's a bunch of there's a bunch of houses available for rent, and they're all advertised in this website, sort of like we have Trade Me, but well, this website in Gopherland that lists those ads. And at all times, there's a bunch of homes available for rent in this website, but at the same time, at all times, there's an army of gophers that want to get these homes before you. So every gopher in this Gopherland is using the same base algorithm to sort the homes such that they get the homes that they like the most first, and they go visit that homes in that order. And Gofi is also using, but now he really has to move, so I'm asking you to help me, optimize these algorithms to sort it faster so that Gofi gets the best homes first. Are you going to help me? Otherwise, this is going to be a really short presentation. Yeah. Okay, you didn't raise your hand or anything. I'm going to assume that you're okay with helping me. Cool. So first thing we have to do is talk about distance to Gofi's office. So we have the map. This is an idea of what the map of Gopherland looks like. And as you can see, the particular thing that's a little bit weird is that the map works like this. We have intersections, and the intersections are numbered. Now, every ad on this website has, a home. This home, if it's around here, for example, then the ad is going to say that its location is intersection 2. And that's how we understand where the homes are in this list of available homes. So there are going to be numbered intersections there, and Gofi's office is in intersection 0. All things being equal, Gophers prefer to live close to their home. Cool? Does that make sense? So we want to get a home, or we want to sort the homes such that we choose the homes that are closer to Gofi's office first, far away after those. The other thing is rent price. All things being equal, Gophers prefer to rent the cheapest home possible. But now we have a problem. Like we have two criteria, distance and price. So what we're going to do is, what Gophers decide to do in this base algorithm that they use is that if a home is advertised as being $115 a week, and another one is $136, they're in the same price range, so they're going to choose the place closest to the office. So distance matters within the same price range. The price ranges go in the hundreds, so 100 to 199, 200 to 299, and so on and so forth. Cool? So if we have two homes in the same price range, we choose the one that is closest to Gofi's office or to the Gopher's office. The last thing, there's a thing, council of Gopherland, and the council can approve the homes or disapprove them. Now you can still rent the disapproved homes, but that's illegal, so Gophers don't want to do that. That's the most important criteria is we want the approved homes first, the disapproved homes last, right? So we have three criteria: council approved, price range, distance. That's all we need to sort the homes. Now, how we're going to help Gofi? As I said, every Gopher uses an algorithm to sort the homes, and this is without the actual calculations. It's pretty simple. In the code, it's going to be as simple as this. So we have loop over the slice of ads that we scraped from this website, and then we're going to enrich that slice by adding the distance that we're going to calculate the distance from Gofi's office, which is 0, the intersection 0, and the intersection of the ad in this iteration of the loop. We also need the map of Gopherland to calculate the distance, right? It's going to be some sort of data structure that hopefully is very simple. Once we enrich the slice with all the distances, we need to do the last thing, which is the final in-place sorting of the ad slice. As you can see, it doesn't return anything, so it's an in-place sort based on, sorry, that's wrong. Sort based on price, distance, and approvedness. Unfortunately, I'm not going to recompile in my server, so it's going to be wrong in the actual code, but yeah, we can accept it, hopefully. So as you can see, we have the slice of ads again, and we have this council approved. It's the API that the council, was so good to help us with the actual API. That's just a function that receives an ad and returns true or false, approved, disapproved. Cool? That's the code. And the implementation of calculate distance and sort blah, 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 is the thing that we need to make more efficient. So you guys go to, this is basically algorithm optimization, which can be boring, but I have two elements to make it a little bit funner. One, we're going to use Golang plugins, and that's just awesome. And the other thing is we have a UI for seeing if we're doing good or not. So let's just fine print before we start. For our optimization, when we code, we can't use the standard lib. The only thing I'll allow is random number generation if we need it. I don't know if we need it, because Otherwise, that would be probably a little bit boring to read from the view random. And the other thing, the prices of the homes are within $100 and $1,000 inclusive. Cool. So how many ranges are we gonna have? 100 and 1,000 and ranges of 100. How many? Yes. Thank you. 10. That's it. Let's see the UI. I didn't actually prepare, so we need Docker. Okay. Tell me when you can see. I'm going to need 3 of these, but yeah, we need to open something. Source. Run, Gopher, run. That's it. So I need 3 of these. You would hope they all get cleared. Should be here. Sorry, I get fired. Yeah. Okay. Let's deploy this. Cool, we have a Gopher server, something. So let's open it. Reload, yeah. Cool. So there is a base and a target. That's what every Gopher is doing right now. And that's, it's a metaphor, right? It's like a run. And whoever, gets first, then it gets the best homes first. And then the target is what we want to get our code to. Cool? So let's see. Cool. So we want to get as fast as target in terms of resolving this sorting thing. And there's a very important thing. I don't know if you can see it. Maybe I'll make it a little bigger. Oh, yeah, that happens when I do that. You see the OK below here? That means that whatever it is we did actually produce the right, the right sorting result. Otherwise, we can make something that is really fast. We can make something that's really fast, but that doesn't actually sort the thing in the way that we expect it to. So Goffy is going to go to a place he doesn't want to go to, maybe this illegal place. All right. I said we're going to use Golang plugins. So let's see what that looks like. We need to copy and paste the base and try to make it better, right? So let's see what we have here. We have a folder in there called plugins. Do you see it? Okay, we have a folder called plugins. And we have 2 plugins in there, base and target. So what we're gonna do is open it on the best editor in the world and duplicate base and call it meetup, and that's us. We need to change the name of the plugin to meetup. Thank you. Is that enough? As you can see, those are the calculate distance and sort base. Those are the functions that we need to change. But I need to compile this plugin and see if it appears in the UI. Now, please note that the server is still open, and I'm not going to close it, but I'm still going to compile and run Go code. Awesome. All right, let's go to meetup. Compile. Yep, I can't do that, right? Why? I compiled. I go build, right? Why can't I compile? Nope. Because I'm on a Mac. Go plugins don't work on Macs. Okay, so I need to go into some sort of, I need to go into an Alpine Go or something, right? Shut up. Cool. Now we can compile. That's a Go build, basically. Okay, it compiled. So now let's go back to the UI. Reload. And now there's a meetup there that should be as fast as base. In practice, I don't know if it's going to be exactly as fast, but it should be within the order of magnitude of base. It's a little bit slower. Well, I'm going to make it a little bit harder, but it's okay. As long as it says that it's doing the right thing, I'm good. Cool? So we didn't restart the server, right? That's why we're using Golang plugins. Okay, let's look at the code. We need to implement these two functions. Calculate distance, going to be really, really boring. Now this first, look at the map for a second. What do we need to obtain to understand to get the full information for the map of Goverland? So we need some information about each one of these intersections. And what information do we need? For each one, we need to know which other intersections it connects to or edges. So this one, and this one for 2, this one, and this one for 5. And the other thing we need to know is like how far it is to get to each one of those. So let's go back to the structure. The first slice is the slice. Each one of those elements is each one of the intersections or vertices on a graph, right? Each one of these. And for each one, we need a slice of edges. Does that make sense? Now, we need two things from each edge, which is where does it connect to and how far it is. V is the other intersection, which vertex it connects to, and D is distance. How far is that destination vertex? That's the graph. Cool? Now, it is currently being solved with some algorithm called Floyd-Warshall. Does anybody know what Floyd-Warshall is? I don't. Nobody? Looking at you, Jonathan, no? Cool. Well, that's what we're trying to figure out. Like, we need to make it faster, that's for sure. So, Floyd-Warshall, I've tried to explain Floyd-Warshall to a mirror, and it's not cute. But it is not necessary to understand what it does. Just look at the algorithm for a second. Look at the first line. It's calculating some sort of like slice of slice. Like D is a distance, because at the end you can see that it returns the distance from source to target. So that this matrix is going to have vertex to vertex. What is the distance? Cool. And doesn't matter how it's doing it. You can see that at the end is going like nested for loops over the same, over the whole graph. So can somebody tell me what the time complexity of this algorithm, Warshall algorithm, is going to be? Anybody? 3 nested for loops? Come on. No? Okay. Yeah, O n cube. Yeah, that's it. Yeah. There's also some, yeah. Anyway. So yeah, that's going to be O n cube. Now, when we say calculate distance, we're omitting some term. In that calculate distance is something missing. Where are we actually calculating when we calculate distance? So is there more than one way for getting from I to J? Yes, we're calculating shortest distance. Does anybody know like a very common way to calculate shortest distance? Dijkstra? Yes, Dijkstra. That sounds cool. So does anybody know what the time complexity of Dijkstra is? What? Well, it's complicated, and I don't really care so much. It's not complicated. It has 2 parts because it depends on the number of edges and the number of vertices. But I'm going to implement a much simpler version of Dijkstra, which is O(n) square, which is worse, but we just want to beat the other gophers. We don't want to get a PhD in graph theory. So simple Dijkstra, let's call it. Let's remember quickly how Dijkstra worked. We're going to make a simple example. Let's write Dijkstra because that's just awesome. Sorry? Is it like this? Am I getting it right? Is it okay? Okay, so a simple case. Hello, sorry. A simple case, we have just 3 nodes. this one has a distance of 10, has to be a directed graph, so let's put arrows. And let's say it's 4 and 5. So it's probably cheaper or shorter to go this way than this way, because we say 1 is 9, not 10. That's the simplest example I could come up with. So what do we know? We have a source. We have a source node and a target node. In this case, I want to go to C. Sorry, I thought it was already set. We didn't know. From A to C, and we have information about the graph, which apparently is a slices of edges. We're going to need two more things. We're going to make a slice of distances. And when I say distances, it's distance from the from or to the source location. That's what the distance is. And we're going to need a map of visited nodes, which is going to start empty. We're going to have an initialization stage. We're going to assign for every node a very large number, like infinite. That's a number. Except for the source. The source is going to have distance 0 because we're already there. I think. And then we're going to have a main loop. And our main loop is going to go on while this condition is true. While the length of the visited map is less than the length of maybe this one or this one. Doesn't matter, right? They have the same length. You have one element for each node in the graph. Okay, that's all we need. Now the algorithm looks like this. While this is true, we're going to look in this slice, the distance slice, for the smallest element that is not visited yet. In this case, the first case is always going to be the source node. So we mark it visited. And now we look at using the information from the graph. It's going to be this slice in here for the first element. We look at the connecting, at the edges that start from A. So it's all the entries in here. Just loop over this. We're going to have two of them. So we go over the first one, and we say that the distance to that B node from the source is whatever we have here. In this case, it's always 0, and this distance 4. And then we ask the question. This is the extra point. Is 0 plus 4 less than infinite? Answer is yes. Then we override that, and we change it to 4. We move on to the next edge in this loop. And it goes to C. Now 0 plus 10. Is that less than infinite? Yeah. We're done with all the elements in this slice. So we're going to do the algorithm again. We go over the loop again. Visited is less than the length. We only have 1, and we have 3 entries here. So we look for the minimum element here that is not visited. In this case, it's 4 because this one is visited. So, sorry, not 4, B. 4 is the minimum. Yeah. Where are the nodes coming? Sorry, at the edges coming from B, only one, this edge in here, it goes to C. Now we say distance to the source from B, 4, plus this 5 in here is 9. Is 9 less than 10? Yes. So we override. Sorry, yeah, we mark B as visited as well. Please. It's more important not to forget that in the actual code, because otherwise it runs forever. Is there any other edge coming from B? No. There's nothing else here, so we move on. Run the algorithm again. We have 2 here, 3 here, therefore we move on. Keep going. The minimum element that is not visited is now C. Look at the edges coming from C. That slice is going to be empty, so we're done. Because on the next iteration, this is going to be 3 and this is going to be 3, therefore it's not less than, and we're done. When we're done, we can ask, what is the distance? The numbers in here are the distance from the source node to any of these nodes. We care about the target one, so we ask, what is the distance from the source to target? The answer is 9. That's the algorithm. Can we code it? Yes? I'm not going to code in this thing because it looks complicated. So I'm going to create Okay, mk there, test. So let's write some Go code. Does anybody know how to do table-driven tests? Okay, let's go. What do I do? Test case type, okay. Can I do it like anonymously? So what do we need? We need I, J, that's the source and target nodes. They're gonna be ints. What else? We need the graph, which is a slice of slices. I don't have this type. What does it have? Vertex. Let's make it uppercase so that it compiles on the other one. Vertex and distance. They're both ints. Now we have our type. What else do we need? Expected distance. Let's go with one example because we don't have time to do everything. So the only example, we need to replicate what we see there. So I is going to be 0. J is going to be 2. Wow. Sorry. I guess this is 0. This is 1. This is 2. Because I don't, slices are numbered like that. Sorry. So we have a slice of edges. Let's go explicit. I know I can elide those types in here, but it's easier this way for me, I guess. We have 3 nodes. Each one of those nodes has a slice of edges, and here we're going to have edges on the first one. On the second one, we have 1 edge, and the third one, we don't have edges. Cool. Now we need to put the vertex first, the distance after. So the first node goes to 1 and to 2, so 1 with 4 and 2 with 10. That was complicated, sorry. 2 with 10. If I make a mistake, please let me know. Second one goes to 2 with 5, and that's it. Here we have a test case. I'm missing a comma though. Let's run it. Yeah, so our actual value is going to be running Dijkstra. I don't have a function yet. Damn. It's I, J, graph, H. Does it return something? Yeah, and it returns 0. Now I have a function. Extra. T.I, T.J, T.G. A stands for actual. If T.expected is different from T. Sorry, we're missing the expected here. 9. Sorry, actual. Then I'm unhappy. Of those 3 elements should have been that value, but was that other value. Yeah? Cool. And otherwise, I'm very happy. Sorry? This one. Yep. Hopefully I won't see that. Let's implement Dijkstra. So what do we need? I said we need 2 things. It's called the distances slice. What is it? Int. Length is the length of the graph, right? We're going to have 1 entry per vertex. We can also set the capacity. This is now going to save a lot of processing power. And then the visited map. What's map? We have the int, but we don't have anything interesting to store about it, other than the fact that it exists in the map. So I'm going to make it as a map of int to empty struct. And now the initialization should be going through the elements in the graph. Is it? Yeah. So, no, I can't use the I, can I? And what are we going to do? We're going to set the value for the distance to infinite. I don't want to use math inf. I'm going to go, we can't use the standard library anyway. So I'm just going to go like with the max int 32. Yeah? But if k equals the source node, then the distance is 0. Now the main loop. What does before I forget, let's add return distance to the target, right? That's what we want, the result. So the main loop, what does it do? I have a cheat sheet there. The length of visited is less than g. And what do we do here? This is the Dijkstra moment. Okay, so this is the part that optimize. The thing I'm going to choose here is like getting the smallest distance here. That can be, we're going to loop over the distances every time. So it's going to be like ON every time, but we could potentially use priority queue or something to make it quicker. But I'm not going to do that. We need to store that somewhere. Let's call it min and min ith element. We need values for that. Let's start with a large number for that min. No? Yeah. This one doesn't matter. We for loop over what? The distances, right? Yeah? Sorry, we need the end. If what? I'm forgetting something very important, right? We need to, no, I'm not. Okay. We don't want to use an I. That's the problem. Okay. We should probably call it min k. That's more like it. Yeah? Does that get the smallest one? What is missing here? Why is that not going to work? Is it too cryptic? Well, the node has to be has to not be visited. So I'm missing something here, definitely, right? So not visited and distance is less than the minimum. Now it looks all right. Now we set that node as visited. And now this is the Dijkstra moment. Now we selected the node, right? We're in the initial, we are in here and looking at the edges of that element. Cool? So it's going to be another for loop, I guess. So we're going to loop over the edges of the selected node. Yeah? And what do we ask? It's going to be a question that is something that is less than something, right? So that we can overwrite. What is the question? The question is, if the distance, we have this min is this distance here, and we need to add to the distance distance of the edge, right? So if we add edge dot distance, we want to ask if that distance is less than the one that we currently have computed for that edge. That would be E dot B. That's the vertex, destination vertex. Cool. If that's the case, then we update something. We update the distance that is currently too long. And we update it to this. I think that's it. Now, we'll run this and hopefully it works. Dijkstra. Okay, and find K where? That's right. Where's the K? It's min K. Yes! Dijkstra works. All right, so we have Dijkstra. How hard would it be to put that into our plugin? Sorry, there. So we need to replace that Floyd Warshall with our Dijkstra. We have our Dijkstra here, and edge is T dot edge, I guess. Let's see if that's it. Yeah? What do you think? So we're not going to stop the server. We're just going to recompile the plugin. Cool? Compile. Please. Okay, now's the moment. If this doesn't work, I'm going to be really sad. Reload. Please go faster and say okay. Wait. Yeah, okay. Yeah, cool. Yes. But it's still not as fast as target, right? We need to do one more thing. Hopefully not as involved as Dijkstra, but maybe not. Okay, last one. All right, so now we have, I don't know how this API works, but the ads now have the distances in them. Somehow, the server actually knows how to put the distances that we've calculated into this slice of ads, ads for homes, right? So now we have to do this implementation, sort based on price, distance, and council approved. We have a slice of ads. Let's look at that struct. It should be simple, otherwise it's not made in Go. So we have a price. That's the one that we put in ranges of hundreds. The distance that we calculated, and the location that we used to calculate the distance. We don't care about the location anymore. So we're going to use these two, and the council approved function. And that's a function, that's an API from the Council of Goverland that you give it an add, so an instance, an element within that slice, and it's going to tell you it's approved, it's not approved. We have those three criteria: price, distance, and council approved, and we have to sort accordingly. Cool? At the moment, the sorting is happening with bubble sort. Does anybody know what bubble sort is? What's the time complexity of bubble sort? Let's look at the code. So, can everybody see that? So it has two nested for loops. What is it? Yes, it's O(n) squared. But with a it's O(n) squared, but if a council from anywhere in the world except somewhere in Germany, gives me a function, gives me a function that answers some question, I'm not going to expect that to be particularly performant. In this case, it's not at all a time sleep that always returns true. But in this case, you have to do it 4 times on every iteration. So I think it's going to be more important to make that only once. Potentially, we can just slice over the ads and just ask council approve and then store that somewhere. Much easier. But let's assume that we can't do that. So sorting. Yeah, this is pretty simple. Let's see what it does. So first, it gets rid of the council approvedness problem. For 2 elements, I and j, I being always smaller than j, Oh, sorry, left and right is different for you and me, sorry. So for two elements, they can either be in the right or wrong position in terms of, well, no, sorry, but in terms of the council approvedness. If the element on the left is council approved and the element on the right is not council approved, then they're in the right order, so we can continue with the next iteration. Yeah? Does it make sense? If the J element, so the one on the right, is approved and the one on the left is approved, then we just swap them and we can continue. If we didn't exit the loop or went to the next iteration on the loop up to there, then we don't care about that council approvedness anymore. So that's what it's doing in terms of that the main sorting criteria, the council approvedness. Then it's calculating price divided by 100. That's a really clever way of getting the price into price ranges. So if it's 100, which is the minimum value, 100 divided by 100 is 1, so it goes into the first range. Cool? Yeah, and Go divides, it's the truncates to the left. So yeah, does that? Yep. Okay, so that's the price range. Then we ask the question, if the one on the left has a greater price range than the one on the right, then we can swap them and we're done. The same price range, then it matters which one is shortest to Gopher's office or to any Gopher's office, right? So if the one on the left is farther away from work to the Jth, then we need to swap them. Otherwise, we don't do anything on that iteration. So that's bubble sort for you. Does anybody know of a faster, any other sorting algorithm that has a better time complexity than bubble sort, than O(n)² squared? Who? Any other one? Quicksort? Sorry? Merge? Yeah. I'm not going to tell you that. So, okay. Yes, I have many. Insertion sort is not fine. Then if I have more, then what should I use? Sorry, I forgot in the fine print. We don't use coroutines here. It's too complicated. So we have quicksort, merge sort. Merge sort is not in place, but we're gonna do something not in placey. Anyway, anything else? Okay, cool. There's also heap sort in that list. So what is the complexity of time complexity of merge sort? And log n. What about quicksort? I recommend that we use quicksort because of cache locality. It's actually faster in most implementations. Wow. Anyway, Go will sort using, well, depending, it will downgrade to insertion sort as Jonathan will put, but it's mainly going to do quicksort, and also MySQL, when it does group by, it sorts using quicksort as well. So let's go with what the giants use. Anyway, okay, so if we use quicksort, we're going to go to n log n rather than n², so that's good. We're going to beat the Gophers. But I think we can go a little bit better than that. Now, is there anything about this data that would, that you think that there might be a more efficient way than n log n for at least part of the sorting? Nobody? So, yeah, that's a good idea. So we have, let's imagine that half of them are council approved and half of them are not. So what can we do with that? Oh, buckets. What kind of sort starts with bucket? Bucket sort. What's the time complexity of bucket sort? You go only once over the elements, so it's O(n). Yep. Or if you go twice over, it's also O(n), no problem. As long as you don't go n times over the thing. So yeah, so we could use the bucket sort, which is O(n), for the council approved, but hey, price ranges into 10 buckets. do like, 10, or actually 20, right? Because it's just a multiplication of the 2 and the 10. Now, of course, within each bucket, we still need to sort them. And, the most efficient way that, arguably, I don't know, would be quicksort. So we can do both. How does quicksort work? This one should be easier, please. One, 4, 3, 2, 5. I didn't pick that at random. So what do we do? Magical word starts with P, ends with ivet. So we select we're gonna have 3 pointers. We're gonna have a left, a right, and we're gonna select a pivot randomly. Why do we need to select it randomly, Jonathan? Why do? Yeah, cool. Wikipedia told me that if you choose the pivot at random, you're really, really likely to have a n log n runtime. Otherwise, it can degrade to, if all the elements are equal, it's going to be O n squared. That's regardless of choosing the pivot, sorry. So I'm going to pick randomly the one in the middle. In the actual code, we can use, math run. So what do we do? The first thing we're going to do is we're going to take the pivot and put the value at the rightmost element. So we're going to do a swap here. By the way, quicksort is in place. So it's only doing swaps. That's why it's so useful for library implementations. Like go use it, I think. So we swap those elements. So what do we get now? 1, 4, 5, sorry, 2, 3. But the pointers still point to the same places, right? I'm gonna stop talking about the pivot now, but the pivot is here now. It's just that it's pointed to by R. So now, what we're gonna do is we're gonna loop over the elements up to where the pivot is, so all the other elements, from left to right. And we're gonna ask the question, is the number, current number, less than the pivot? If it's greater than the pivot, then we're not going to do anything about that. But if it's less than it, we're going to move it to the left. Now, it's not moving it to the leftmost element. It's moving it to where L points to. Let me demonstrate. We start with 1. Is 1 less than 3? Cool. Then we're going to, what do we do? Then we move 1 to the left, but in this case, it's already there. The only thing we're going to do other than that, when we do the swap, we're going to increment L to the next position. Is 4 less than 3? No, then we don't do anything. Is 5 less than 3? No, then we don't do anything. Is 2 less than 3? Yes. So we're going to move it to where L points to. Swapping. Swap. 2, 5, 4, 3. And then increment L to the next element. Yeah, that was the last one too, right? So we're done with the loop. When we're done with the loop, we're going to pivot where we finished with L. So we're going to swap L with position of the pivot. We end up with 1, 2, 3, 4, 5. That's a miracle. It doesn't usually work like that. And the pivot is here. Now there's a chance that it's very likely that the elements to the left and to the right of the pivot are not sorted. In this case, magically they are. But the only thing that we do know for sure is that all the elements to the right of to the left of the pivot are going to be smaller than the pivot. And all the elements to the right are going to be equal or larger than the pivot. So the pivot is in the right position. We don't need to move it further, which means that we can potentially parallelize the algorithm, but the important thing is that we can continue to quicksort this sub-slice and this sub-slice, and we're done with this. And when we're done with those, we're done with this sorting. It's done. Note that, well, in a perfectly balanced world, there will be the same number of elements to the left and to the right, which means that every time that we proceed with the nested iteration of quicksort, it's going to quicksort half the elements. And that's what makes it n log n. That should be easier to implement. So, quicksort. We can borrow the testing thing, right? So in text, right? And it doesn't return anything. Yep. Thank you. We can't do equals in here, can we? Equal t dot what? Yeah. Let's go here. There. Cool. Is that it? What am I missing here? Comma. Okay, how do we do quicksort? We need three things here, L, R, and P. And we're going to need some randomness. L equals 0. R equals the last element. And the pivot is going to be rand-inten of the length. Those are the three elements that we need. So the first thing that we need to do is we need to put the pivot in the last position, right? So let's swap the pivot with the right. And now we don't care anymore about the pivot. That's what a swap looks like. Now what do we do? For what? We might need to do swaps, say we need to have some sort of I. No, that's not right. We can't go over the pivot. Okay, now it's right. What is the minus, the less than question? Is the current element, if it's less than the pivot, which is in R now, then swap them. And what else? What else? We need to increment L. No, this is not right. Yeah. Sorry, we need to swap it with L, not with R. Cool. And then when we're done, is it done? What? Oh, thank you. So the pivot is in R, and we need to swap it with L. And now we do the recursion thing. We're going to have two Q sorts. What are we going to Q sort? Right. Up to the pivot position and from the next one, because the pivot is in place. and this is going to run forever, right? We stop. Zero or I guess one, right? Because if there's one element, we don't need to keep going there. We're not going to be able to swap with anything. What? You mean here? If L, keep going. Oh man, you should have told me that before. So if L, yeah, don't worry about that. The iteration is gonna start, it's gonna end immediately. Don't worry about that. Cool. Yeah? Is it gonna run? Yes! This never happened. So can we put this in the, well, not yet, right? We need the bucket sort part. So what bucket sort? That we don't need to do this for bucket sort. It should be incredibly easy, right? Anybody can do it. It was the one that we did here. Bucket sort. So in this case, the examples, let's prepare them with hundreds so that we don't have to change it later. So it's 100, maybe 200, and then 110, so that it's in the same bucket, maybe in the wrong order, which is fine. And 230. We want them to be sorted. By the way, the sort is not stable, but it doesn't matter for our purposes. That's what we want. Now the bucket sort is not in place, so we need to make it in place. That's the only interesting part of it. Yeah? So what's the bucket sort look like? We're going to need buckets. Buckets. Mail. And each one is going to have size events. It's going to have 10 buckets. Is that it? So what's the bucket for a number n? So n divided by 100, and we could optimize it like -1 so that the first bucket is 0, not 1. I think that's it. So we put it in that bth bucket. Now we have the elements in the right buckets. We can't return anything, so we need to put them back in NS. Now, is that going to work? Like if we override the context of NS, is it going to work? Is it? Well, it's the same amount of elements, so I'm sure it's going to be within the capacity. It's the same elements in a different order. So, okay, we loop over the buckets. And for each bucket, we also loop over. Can we do that? Yeah. And we need some other thing to increment. And that's it. I think we can just sort. Very simple. Now you don't be fooled by this. That's the same amount of element. This is still ON. So this bucket sort is going to be ON. It's much faster than that quick sort. Yep. Does that work? Let's see. What? Come on. Yes! No, this is amazing. Okay. How do we do this? So we need to replace that bubble sort. So we're gonna use bucket sort instead of bubble sort. But we have 20 buckets, not 10, because we have the council approved to take into account now. NS is actually you're gonna have to replace NS with adds, and it's a slice of adds. Yeah, and then this is an add, not an in. And this is the price. I think other than that, like this part of the bucket sort should work, but we have 20 buckets and we're only filling it in 10, so we need to add something here, right? Something like the council approvedness, which is going to be an int. But how do we calculate it? Let's say that is 0, start with. So 0 would be if it's council approved, right? Because it means that we're going to put it in the first bucket, and the first 10 buckets. That's if it's approved. So we need to call that council approved function. For that add, if and if it's not approved, then we plus equals 10. Is that going to work? And then we have our 20 buckets rather than 10. Yeah? Cool. So we dealt with the council approvedness and the price range already. We still need to order based on the distance for each one of those buckets of council approvedness and range, price range. How do we do that? This BS bucket, BSI, is the bucket that has a set of ads of the same price range and the same council approvedness. So we can sort this one. So we don't have that function, but that should be it. I'm really scared this is not going to compile. Sorry. Okay. Too many NS's. Let's keep it. Is that right? And what do we need to change? I think it's just this comparison, right? Because the rest is swapping. So the comparison should be the distance, not the add itself. Or maybe that's just it. Well, let's see if it compiles. We need to compile our plugin now. Did I change the invocation? No, I didn't. Okay, compile. Okay. Cannot use types as type in. I forgot something in 35. This one, because that's slice events. Anything else? Cannot even. Oh, that's it. Let's see if it runs faster. You can get pizza and stuff. Say okay. Okay, yes! Yep, so thank you for helping me, help Gofi find a home. I found a home, so yeah, but it was still more expensive. So thank you. Thank you. Any questions? Yep. Oh, sorry, once again, we have a mic.
What's going on behind the scenes when you're compiling that plugin? Because that's quite interesting to me.
Thank you, thank you. That's a very, very interesting question. Go plugins production. Please, ironically, please do it at home. You know what I mean? Don't do it on yeah. There's a whole bunch of things that make it not awesome, at least for what my idea of simplicity. So let me rant a little bit about Go plugins, and that it will be evident how the thing actually works behind the scenes. So, okay, so we have those plugins. The code should be really simple. Sorry. Yeah. So the compile that we saw before is basically Go build. Everybody see that? Come on. Yeah. So that's the Go build that is compiling the plugins. It says build mode plugin, and we have to add this thing. It has like the current timestamp. Hopefully, we will not compile twice in the same day. But if we did, it would probably, be possible because compiling in Go many times takes less than a second. That's awesome. I love Go. And then we also have to change the name. We have to change the name of the binary that we produce. So see, we have to change the name of the binary that we produce, and we have to change this internal location of the plugin, sort of like a logical location of the plugin, every time that we compile. Otherwise, it doesn't work. If we don't change any of those two, when we try to load it in the server, it either panics or it says that it's already loaded. That's beautiful. Then the plugin itself is quite The plugin itself, it should be in the plugins directory. Is 2 megabytes for the code we wrote. It's probably holding the runtime there. I don't think we need a runtime for a plugin, right? The runtime is already in the executable. I looked around in the issues for Go plugins, and the guy, I think it's called Croshaw, the guy who's working on Go plugins, has had the issue open for like 2 years to just remove that runtime, unused runtime from every one of those plugins. But he hasn't come around to it yet. He's doing perfect work, but he hasn't come around to remove the runtime from those binaries. So anyway, every time we're compiling with Go build on that main.go, now the main.go looks like this. The things that are going to be exported from this plugin are all variables and functions. I need something else to make this code work. What is it that is not a variable and is not a function? It's right here and here. Sorry? Yeah, structs and yeah, other things. Those are not exported. So how do I solve that problem? The way I solve that problem is by adding another package with the types. And I import the types in both the server and the plugins. You have to do it that way. The other way is, you can use reflection. That's I wouldn't. If I'm using Go, I don't want to do that, right? Otherwise, I would, I don't know, use Scala or something. New types with, yeah, if you use reflection. I mean, on the server, I wouldn't know what the type looks like, so I need to inspect it. But yeah, you can. So, yeah. If you, so you're asking if the type is only used within, can I use it? Yes, it's valid Go code. You can do whatever you want. Yeah, so as you can see, the things that I'm exporting from the plugin have uppercase names. That's, you know, no magic. We already know, right? The things that are uppercase can be exported, and that's what we're doing. If we look at the server code, I just want to show you that it's really simple. There's only 3, other than the types.go, there's only 3 Go files, and one has the sample data only. The other one is just an endpoint. It exposes the results for the UI. And then there's a main Go. This is the code that runs the plugins that we made. As you can see here, this is exactly the code that we had in the slide, the for loop and the sort. The only difference is that it's being very carefully benchmarked. Yeah. And here it's validated against a sorted dataset. And then the output is served through the endpoint that we created. Loading a plugin looks like this. We're looking into the plugins, looking for plugins. And for each one of the files, we see if it's a plugin, we look for an SO file. And once we have it open, plugin.open, that can panic. We look up the name of the plugin and the 2 functions. We need to cast those functions. So here's the casting. And the string. By the way, the strings, all the variables are casted as pointers. That's finally, we append it to a slice of plugins. And then for every plugin, we run the plugin. That's the code. Can we get the mic? Okay. The question is, what version of Go am I running? Is it because of the Go plugins thing? So I'm running the latest version of Go. No, sorry. Today is 1.10, so I'm not running the latest. So apparently 1.10 has the plugins on Darwin. We discussed the things that are new in this 1.10 today in the Slack, and that didn't come up, but we're not all smart. So. Right. Yeah. But anyway, 1.8 had support for plugins, but apparently something broke, so they removed it. So in 1.9 it's not supported on Darwin. Anything else? Pizza time. Okay, cool. Done. Thank you.
Thanks very much, Mariana. That was amazing. Pizza and bricks now. Just so you know, we're starting to run these meetups once a month now. I think we're alternating with Ben, and I think Evan from Ben is going to host next month. And we're trying to do live streaming of meetups for the benefit of people around the country. Not that many of them, but we're giving it a go. I'm not sure how well this worked quality-wise. The talk was good quality, but we're going to keep trying. Okay, thanks very much. Peace out.